Now the second type of rate law is the integrated rate law. This rate law is determined by graphing, and it is concentration versus time data. If the reaction is zero order, then the time versus concentration graph will be linear. If the reaction is a first order reaction, then the time versus natural log of the concentration would be linear, and if it is a second order reaction, the time versus 1 over the concentration would be linear. So really what you need to do with the data, the concentration versus time data, is create the three graphs, and then whichever one most closely resembles a line, whether it's time versus concentration, time versus natural log of concentration, or time versus the reciprocal of the concentration, whichever one is most linear then determines the order of the reaction. So let's take a specific example. We'll take hydrogen peroxide. So concentrations were recorded over time, and it looks like the reactant, H2O2, is decreasing, which it should be. And the problem is to find the integrated rate law and then also calculate the rate constant. So, a graphing calculator to graph all three of these would be excellent, and then looking at the correlation coefficient, which is the R squared, when you do the regression, the closer the R squared is to 1, the more closely the points are aligned to a line. So, as in any integrated rate law, you want to do three graphs. So you want to take time versus the concentration and graph it. Notice the R squared value there is 0.8891. Then you want to take time versus the natural log of the concentration. Notice that the R squared value here is 0.99978. And then you want to take time versus 1 over the concentration of hydrogen peroxide. And notice here that the R squared value is 0.8723. And again, you're looking for the correlation coefficient, the R squared, that is closest to 1, because then that means that graph is the closest graph to a line. And that second graph that we created definitely was, just by looking at it, the closest one to a line. So the winner is time versus the natural log of the concentration of H2O2. So therefore, that means the reaction is a first order reaction. So if we were to write the differential rate law, remember that was the first rate law that we looked at. If it's first order, the exponent on the H2O2 will be a 1, so its rate equals K times the concentration of hydrogen peroxide raised to the first power. The integrated rate law, however, is written in the y equals mx plus b format. So ln of H2O2 is the y, the negative kT is the mx, and then the ln of H2O2 naught, which means initial concentration, that of course is the y-intercept. So then, how do we determine the rate constant then for K? What's the easiest way to do that? Well, there's two different ways really to do that. The first method is to calculate the slope from the time versus natural log of hydrogen peroxide table. So that would have been the slope that was generated when the regression was done on time versus natural log. So if we go back to that, there's the slope. If we just simply took the change in H2O2 over the change in time, the slope would be negative 8.32 times 10 to the negative 4th, and the unit there is seconds to the negative 1. Now remember that with this particular order, whatever the slope is, the K is actually the opposite to that, because notice there in the y equals mx plus b version, the negative kt, the slope is actually negative K. So the K therefore equals the the negative of the slope. So the k, therefore, is 8.32 times 10 to the negative fourth, and again, seconds to the minus 1. Now, as I said before, you can also just simply do it from your linear regression. If you look at your linear regression there, when you did that in your graphing calculator, the slope is the letter A, so that's the negative 8.35 times 10 to the negative fourth. And then again, because of the order of this reaction, of course, being first order, there's a negative k there in the equation, so therefore the slope is actually, the slope and the k are opposite in sign to each other, so therefore the k is 8.35 times 10 to the negative fourth, and again the unit there is s to the minus 1. So, in summary, and this table is actually in your textbook, this table summarizes the rate law for 0, first, and second order, and it has the integrated rate law equation in the form y equals mx plus b. And notice the big thing that changes is the form of A. So in the 0 order, it's simply the concentration of A. In the first order, it's natural log of A, and then in the second order there, it's 1 over the concentration of A. Keep in mind then from this summary that you simply plot your concentration versus time, your natural log of concentration versus time, and your 1 over concentration versus time, and whichever one more closely resembles a line, that determines the order. And then notice with 0 and first order reactions, whatever the slope is from your regression, the k is the same value but opposite in sign. Notice with second order, because there's no negative there in the integrated rate law equation, the slope is actually the k. And then we will also do some half-life calculations as well. So the equations for half-life there are also stated. If you've ever calculated half-life of radioactive decay, that's actually a first order. So that t to the 1/2 equals 0.693 over k. That would allow you to work with a radioactive decay half-life. But the other half-lives are given there as well.